we are going to discuss roller overhang, that the top rollers and the middle top roller and the front top roller, these two top rollers, if you look at the picture, then you will see that they are really not placed right on the top of the respective bottom rollers. The front top roller is slightly offset forward, whereas the middle top roller is offset backward. And how much they are offsetting backward and forward, the values are already stated in the diagram. Front roller is around 6 to 8 millimeter, that is the overhang we call it, and the back top roller overhang is around 2 millimeter. The point is, why do you do this? This is to actually create a space between the two rollers. And why? Because we have to accommodate the aprons, both the top and the bottom aprons, and also we have to accommodate the condenser, the floating condenser which we place in the front zone. So, that is the main purpose of the overhang. Besides, it also ensures satisfactory movement of bottom and top aprons and also avoids aprons sticking to each other. That is, these are the main reasons why we need some amount of overhang. Now, we will go to the real drafting. One typical drafting image is shown here. So, generally the drafting system that we used on speed frame or roving frame, the roving frames also known as speed frame as well, they are also known as fly frame. The drafting is basically essentially it is two zone drafting system consisting of 3/3 or sometimes 4/4 drafting rollers, but real drafting zones are two. In the case of 4/4 rollers, that could be a neutral zone separating the front and back zone, or sometimes the neutral zone could be in the front also, that is also possible, and that is also known as stabilizing zone, where the draft is very little. The mass of the fiber to be drafted being large, interfiber friction produces large drag between the fibers during drafting. You have to, in the speed frame, because the feed material is sliver, the mass of material is quite large, as you see in the picture. This is the sliver that we are feeding, and as the sliver is getting thinned down, you can see it that even in the front zone the mass is thinning down, but still there is enough mass which is present, and therefore, lot of force is required to stretch the sliver, and the amount of draft that we keep, that as I said earlier, that generally varies between 8 to 10, sometimes it can go up to 12 also, and this draft is distributed in the two zones, back zone and in the front zone. What is also important is the not only the draft, but also the settings. Now, first let us look at the draft that we keep in the back zone, which is also known as break draft. It is not really breaking the sliver in the true sense, it is basically stretching the material a bit so as to orient the fibers. We have to see that there is no effective control which is exerted in the back zone, because there is no guiding device in the back zone other than the condenser. There is no aprons or there is no pressure roller or anything here. So, there is no device by which we can control the movement of fibers in the back zone. The purpose of the break draft is to straighten out the fibers in the sliver so as to ensure an even flow of mildly tensioned, well parallelized fibers into the main draft zone for smooth sliding of fibers. The real drafting is going to happen in the front zone. So, before the real drafting occurs, we want to want to make sure that the fibers are quite straightened out, there is little tension on them and they are parallel with respect to each other, and therefore, little draft is required to straighten out the fibers and to break the mechanical bond that may exist between them because of some entanglement or crimp which is still present in this fiber. And this is achieved in the back zone always, and the kind of draft that we keep, which can vary between 1.2 to 1.4, that much draft is required. That is the kind of stretch that is required to straighten out the fibers. Exact value depends upon whether I am feeding a card sliver or whether I am feeding a comb sliver or whether it is a synthetic fibers. The exact value will depend upon the type of material being processed, and also it depend upon fiber length, fiber fineness, etc. Now comes setting. You have to remember that draft and setting both go together. Setting is basically the nip to nip distance between successive pair of rollers. Typical idea of setting is given in this slide. Front zone setting, fiber length plus 3 to 5 mm. In the back zone setting, the fiber length plus 10 to 16 mm. Now, why the allowance that we keep? It is more in the back zone, which is 10 to 16 millimeter, because the mass of material is more in the back zone. And since the mass is more, the drafting force also will be more. Therefore, to make sure the drafting force is not too high, we have to increase the setting there. The other thing is, if we go about the front zone setting, it must be adequate enough to permit an undisturbed drafting operations. So, we must know what are the causes of disturbance in drafting operations. So, those we should have a good understanding about that, and if we are quite sure about this, then we know that there are many reasons why disturbance gets created, and one of the reasons of disturbance is the presence of floating fibers and their uncontrolled movement, and hence the setting in this space has to be neither too short nor too long. In the case of if it is too short, then you will be gripping fibers simultaneously by the back nip as well as the front nip, and hence fibers may get stretched. Therefore, we have to always make sure that the setting is wide enough not to grip the long fibers simultaneously by both the nips. At the same time, it should not be too long, so that most of the fiber behaves like floating fibers. Though in this case, we have a pair of aprons to take care of these floating fibers or short fibers. The other thing is that the frictional drag between fibers may become too strong to overcome by the drawing force of the front pair of rollers, leading to undrafted portions. So, therefore, too close setting also bad in this case, because if you look at this drafting system, the most of the fibers which are nipped by the front roller, their trailing end is still extending behind the roller, and most of those trailing ends will be gripped by the aprons. So, aprons are trying to now resist their movement, because they are holding the trailing part of those fibers which are gripped by the front roller, and hence a force will develop. The front roller will try to pull them out. Now, while it is trying to do so, if the requirement of force will be more and more if the aprons grip the fibers too tightly. So, therefore, we have to take care of this particular aspect, and what we can do, one is that we have to maintain a setting which is little more than the fiber length, and we have to also make sure that we have to create a gap between the aprons by inserting spacers. So, it is not that we take only one measure to take care of the possibility of undrafted portions. What we do that we create space between the aprons, we also make sure that there is enough setting greater than the fiber length, so that the fibers can be pulled out easily without creating disturbance to the movement of fibers. So, that is how the setting in the front zone is closer or much less in comparison to the back zone, and the front zone setting is also less because in the front zone we have much higher draft, and you have been told earlier that higher the draft, more is the possibility of irregularity, and therefore, to take care of the irregularity we have to make sure that the allowance that we keep should be as short or as small as possible, so that the fibers, especially the shorter ones, do not behave like a floating fibers and they do not move in an irregular fashion. Back zone setting, as I said, it is quite wide in comparing the front zone setting. We have to keep it wide because the mass of material is more there. So, you have to ensure that the drafting force should not be too high to pluck out the fibers from the nip of the back pair of rollers, and hence we have to keep little wider setting. The setting also depends upon the material being processed, that whether it is cotton or synthetics, or whether it is carded cotton or combed cotton. It also depends on the magnitude of break draft, and also depends upon the mass of the material, that is fiber linear density. Higher break draft, if we keep, setting has to be precisely adjusted to fiber length to avoid irregularity, because we have no means to control the movement of fibers in the back zone. Hence, in case we want to keep a higher break draft, then we have to make sure that irregular generation is not too much, and hence setting has to be much precisely adjusted to the length of fiber that we are going to process. If we process coarser fiber, if we switch over from point, let us say 1.2 hank or 1.2 NE to 0.1 NE, then setting should be widened for coarser material, because mass of material is more. As I told earlier, we are again repeating that drafting force will be more, hence we have to reduce drafting force by widening the setting. That is why in the back zone the setting is little more in comparison to the front zone setting. Then comes the roller pressures. Obviously, all the rollers have to be pressed, the top rollers have to be pressed against the bottom rollers. If they are not pressed, there is no drafting, all the top rollers will slip, because top rollers do not get drive from any source. Their source of drive is the frictional contact with the bottom rollers only, and hence there has to be a pressure, a normal force which would act on them, which will only be able to create sufficient frictional force between the two rollers, bottom and top, and therefore, as the bottom rotates, the top one also will rotate. The pressure is maximum on the delivery rollers. Why? This is to ensure effective pulling out of the fibers from the grip of aprons by the front rollers. See, we have to pull out the fibers, the bunch of fiber at any point of time, the bunch of fiber which is gripped by the front roller, their trailing end is still lying in between the two aprons. So, I should be able to create sufficient pull on the fibers to take them out, and this pull only can be created if there is sufficient friction between the two rollers, that is the bottom and top front rollers, and hence we need more force. If you see here, it is 18 to 20 kg force, that is what is required. In the middle and the back roller, if you see, the force is 14 to 16 kg force. Transmitting motion to the fibers, that is why we need, as I said earlier, sufficient force, and avoiding plucking out from its grip by the pull from the middle rollers along with its apron. So, there is every possibility if the force is less here in the back zone, the middle rollers, two rollers and aprons, they are having a firm grip on the fibers, because here the fibers are gripped not only by the nape of the two rollers in the middle rollers, but also by the aprons, and hence a larger part of the fiber length is gripped by the aprons and the middle rollers. So, they can exercise much more pull on the fibers in the back zone. So, if we do not have a sufficient grip on the fibers from the back rollers, then the fibers will be simply plucked from the back roller nape and they will not be drafted. So, they will pluck basically means fibers will move in groups, a bunch of fibers will be simply move out from the nape of the back pair of loaders. So, therefore, to avoid that we have to have more pressure on the rolls, so that the back pair of rollers can exercise sufficient frictional grip on the fibers which are gripped by them. That is why it is there. Pressure should not be too high, as it increases the possibilities of roller bending. This is important also, because ultimately the pressure is going to act on the rollers and there is a chance of bending. See, pressure is acting 24/7, months after months. So, continuous application of pressure can cause the rollers to bend. So, this bending possibility we have to minimize, and what happens that a time comes when the rollers actually bend, the bottom rollers bend, maybe after 3, 4 years or 5 years of use, and then at that time we need to replace the bottom rollers by new rolls. Besides, there will be more load on the bearing, and if there is more load on the bearing, there will be more energy consumption to turn the rollers. So, too high pressure to be avoided because of these reasons. Too low pressures may not give you the right draft that we need. So, we have to find out what is the optimum pressures on the rollers, and accordingly we have to maintain the pressure. So, the kind of pressures which are shown here, that is what is usually practiced in the industry. With this, we close the drafting system session, and thanks very much. We will now learn something else in our next lecture.